Hey guys, Mr. Betts here. I'd like to take a look at a couple examples where we use the fundamental theorem of calculus, particularly the fundamental theorem of calculus as it applies to accumulation functions. So this function right here is an accumulation function. So notice that it's a definite integral, but one of the limits is a variable. So generally, a function in this form is going to have a rate as the integrand, and then the variable upper limit, and this function is going to represent then an accumulation of some quantity. So it's a pretty safe bet that when you see a calculus problem that has an accumulation function defined like this, that we're going to take the derivative of that. So there's lots of different ways that we might use that derivative. Lots of times we will use it to interpret what's going on with the graph, so increasing, decreasing, and then maybe another derivative for concavity. Regardless of what we're going to do with it, I'm going to start by taking the derivative, and notice that ultimately we are going to want the derivative of f here. So I'm going to take the derivative of the left side, that's just f prime of x. When we take the derivative of an accumulation function like this, essentially what we're doing here is we're taking the x and plugging it in for t. That's not exactly what's going on, but effectively that's what happens. So the derivative of that accumulation function is just g of x. And that is the first fundamental theorem of calculus. And then using that, we can plug in the pi over 2. So f prime of pi over 2, which is what we're looking for, is going to be the same thing as g of pi over 2, which we can get just by plugging in here. So we have pi over 2 squared sine of pi over 2. And then we can simplify that as a free response question. We wouldn't necessarily have to, but let's go ahead and do that. So sine of pi over 2 is 1, and so we get pi squared over 4. So again, the key to all of this is recognizing that this accumulation function here, we can take the derivative of that using the fundamental theorem of calculus, and then we go from there. In the second example, we have more of an application problem. So we have a function that represents how fast snow is falling. We're going to make some assumptions here. In particular, the snow is falling and not melting right away or something like that. So this function represents how fast snow is falling between noon and 4 p.m. T is measured in hours, and so that's hours after noon. And R is measured in inches per hour. So notice that R is a rate, inches per hour. So those units, inches per hour, indicate that it's going to be a rate. So we want to write a function S. Okay, so this is what we're trying to do here, that represents the amount of snow that has accumulated between noon and some time after noon. And the assumption here is that this is going to be before 4, because after 4 p.m., this function is no longer valid. So if we just kind of think about what's going on here, if we were to graph this, it's not going to be exactly a square root function, but it's going to look something like that. And the amount of snow that has accumulated is going to be an area. So this area right here up to time x, this should be s of x here, up to time x. So that area being time in hours times the rate in inches per hour is going to give us the number of inches that have accumulated. So that area right there is going to be given by an accumulation function. So the trick here is knowing what the lower limit is going to be. And so we're representing the accumulated snow between noon and a time x. So that's going to give us our limits. Noon is going to be at t equals 0. And our time x is going to be our upper limit. And then our integrand is going to be r of t, which is right here. So that's going to be the square root of t squared plus 1. And then that's with respect to t, because the integrand here, the variable that we use in the integrand, has to match the variable here. So we're finding an area along the t-axis, which is why we have to use the d of t. So in an application problem, if we take an integral of a rate, that integral of a rate is going to represent an area in a coordinate plane. And when we multiply the units of the rate times the units on the t-axis, we're going to get the area units that represent the area, or the quantity that we want to represent with our function here.